Welcome to Homework Lib.
Hi, so for this question, what we are going to do is, first of all, we have an unknown acid for which we have a sample of 50 milliliters with an unknown concentration. So we need to find that unknown concentration. And we know that this is titrated with a zero point 0.3 molar solution of NaOH, and that after adding 50 milliliters, what we have is a pH equal to 12.7. So first of all, before we begin, we need to rationalize what is going to be that concentration of HA. So since 50 milliliters, meaning the same amount, correspond to an excess of hydroxide, the concentration that we are going to find of the acid needs to be smaller than zero point 0.3 molar, just to begin that with. Okay. Next up, this is a monoprotic strong acid. So the reaction starts with H plus OH minus coming from the sodium hydroxide that are going to react and generate water, right? Here you can also write down the equation as HA plus NaOH producing water plus NaA or Na plus A minus in solution. But both of the ways are equivalent, and the only information that we actually need is the value for H plus and the value for OH minus. Okay? So, since we don't know the initial concentration, what we're going to do is start with our ice table, but writing it down in terms of moles. Correct? What is the information that we know? We don't know the amount of mole that we had of X at the very beginning, but we know how much of OH minus we added. The amount of mole of OH minus, it's going to be 50 times 10 to the minus 3, that is the volume in liters, times the concentration of zero point 0.3 mole. So the result is an amount of mole of OH minus equal to 0.015. Remember that this is a strong base, so it dissociates completely in water, so I don't need to write down the sodium, right? So I know that this amount I added to the solution. I know that my H plus is my limiting reagent because we are told that we have an excess of OH minus, right? At the very end of the titration. So at equilibrium, I have almost zero of H plus, and I have 0.015 minus X amount of mole of OH minus. Okay, now, what is the final volume that I'm going to get? The final volume is equal to 100 milliliters, right? Which is zero point 0.1 liters. So what I know is that the concentration of OH minus is going to be equal to 0.015 minus X divided by zero point 0.1. This is the amount of mole that I have divided by the final volume. And I know that the pH of the solution is equal to 12.7. That means that my pOH, by using the relationship pH plus pOH equal to 14, needs to be equal to 1.3. That means that the concentration of OH minus needs to be equal to 10 to the minus 1.3, right? So we can replace that value directly and solve for X. So 0.1 times 10 to the minus 1.3 minus 0.015 is going to be equal to minus x, but we can plug all of this like this and change the signs on both sides. So the final result for x using this is going to be 9.98 988 times 10 to the minus 3, or approximately 1 times 10 to the minus 2. And this is amount of mole. Okay, I'm going to stick with the approximate value. If you want, you can use the full value. So that is the amount of mole that we had at the beginning. That means that the concentration of HA that we had, it's going to be equal to that amount of mole, 1 times 10 to the minus 2, divided by the volume. So 50 milliliters, which is 50 times 10 to the minus 3 liters. Which is a concentration of 0.2 molar. So we know already the concentration of HA at the very beginning, so we can proceed with part B. So for part B, we are told that we added 10 milliliters of the OH minus solution, which is corresponding to adding an amount of mole of OH minus equal to 10 times 10 to the minus 3 liters times my concentration, which is 0.3 molar, which is 3 times 10 to the minus 3. We know the amount of mole of my acid at the beginning, which is 1 times 10 to the minus 2 mole. And we're told that this is a weak acid. We are told that the pH after this addition is going to be equal to 5.03. And we need to know what is the value for Ka, right? If pH is 5.03, that means that the concentration of H3O plus is going to be equal to 10 to the minus 5.03. Let's keep this into account for our reaction. So next up, we are going to consider the reaction of HA plus my OH minus that I'm adding, producing A minus plus water. All of this in aqueous solution. I'm going to do the table in mole in all of the cases. For HA, I know that this is 1 times 10 to the minus 2. For OH minus at the beginning, I know that it is going to be 3 times 10 to the minus 3. That is the amount that I added. And we're going to have 0. And for water, it doesn't. We do not take it into account because it's a pure substance, right? Next up, the amount of change in mole. The limiting reagent is OH minus, so minus 3 times 10 to the minus 3. Over here, we're going to have minus 3 times 10 to the minus 3. And here, 3 times 10 to the minus 3 with a positive sign. So at equilibrium, the value that we're getting is 7 times 10 to the minus 3 something close to 0, and 3 times 10 to the minus 3. And all of this is in mole. But you need to realize in this scenario that we have an acid and we have the conjugate base. So we need to use the Henderson-Hasselbalch equation. Luckily for us, the final volume for both of these are going to be the same. So if we do the concentration of A minus divided by concentration of HA, this is going to be amount of mole of A minus divided by volume divided by amount of mole of HA divided by the final volume. Final volumes are the same, so amount of mole of A minus divided by amount of mole of HA. These two guys cancel out. So we're going to use this fact to get the pH equals pKa from the Henderson-Hasselbalch equation. This tells us that this is the logarithm of A minus divided by concentration of HA. We don't know what is the value for pKa, right? But we know the pH. The pH is going to be 5.03. This is going to be equal to pKa plus logarithm of concentration of A minus is 3 times 10 to the minus 3 divided by the final volume. So we can simply write it down in terms of the moles. Why? Because we did this argument that allows us to simplify that a little bit. So dividing 3 times 10 to the minus 3 by 7 times 10 to the minus 3 is the same as doing 3 over 7. Taking the logarithm of that, we know that this is 5.03 is going to be equal to pKa minus 0.36, 3679, just to be more thorough about it. In this case, actually, we don't need to because we have the pH given only up to the second point. So this is going to be 0.37, rounding up. That means that pKa is 5.03 plus 0.37, which is 5.4. And that would be all for this problem. Thank you very much.